first presentation going to be done by Miss Vidya from Indonesia. And she's, I think, having a good experience on geospatial domain and working with the team who working on the statistics Indonesia. So I think she's having a background of geoinformatics, graduated from Netherlands. We call ITC University of Twente. So I'll give the floor to Vidya for bring your real experience which you have in the ground with your team. Over to you.
Thank you, Kavinda. Good morning, everyone. I'm here with my colleague Ahmad Fauzi, and thank you for the opportunity to share our project regarding the ground truth data for land cover classification in Indonesia. This is the project of Statistics Indonesia in 2022. The production of land cover classification is carried out within 2 years period. And in 2021, the trading data was mainly obtained from visual interpretation, and the output used to determine the target sample location for ground data collection in 2022. And the output from the ground data collection used to reclassify the land cover. As I mentioned that in 2021, we had a project, the land cover classification. The objective is to identify the potential agricultural lands. We use remote sensing and machine learning with gradient boosting tree algorithm. There are two types trading data. First, ground truth data for only rice field class and visual interpretation for other classes. However, we find that there are limitations because visual interpretation raises the uncertainty of the accuracy on the ground, and the quality of sample was highly dependent on the interpreter. That is why in 2022 we reclassify the land cover using ground data as the training samples. And the challenge is how to determine the proper training sample. Because Indonesia is as an archipelagic country, we have very diverse of agricultural lands characteristic, and we have many remote areas or inaccessible areas, and we find difficulty to determine the proper training sample for a particular crops due to the irregular planting system. And in 2022, we conducted the ground data collection. The objective is to obtain the in-situ training sample for improving the classification algorithm. We use Android application as the instrument for data collection. There are more than 800,000 census blocks as the enumeration area, 3.7 million target sample location, and 57,000 field workers. This is the Android application, which named as Wilkerstat. This is not an open application. We developed this application in 2019. Using this application, field worker have to collect photos and geographic coordinates of the target sample locations. As you can see on the image, they have to follow this procedure. First, each field worker has to collect the photos and coordinates in 5 different sample locations within a census block. This is the sample of the target location. Then field worker has to able to identify the land cover in each polygon sample. For example, 1 is a mixed plantation, 2 also mixed plantation, and so on. And then each location then label which fit with the land's characteristic. There are several procedures to determining the target sample location. First, we generate the 100 meters by 100 meter grid cell. Then it overlaid with the 2021 land cover. As a result, each grid is composed of 100 land cover cells, which are consist of either agricultural or non-agricultural land cells. We divided to class, the agricultural or non-agricultural class as follows. The second step is scoring variables in each grid. is used to sort the condition that is expected to be selected. A high score is obtained if it has these following criteria. First, the more diverse land cover class. Second, the majority of agricultural class. Third, the higher percentage of agricultural area and the agricultural classes that contain in a grid cell. This is the illustration result. It can be seen that every grid has this score obtained for this scoring system. Next, the third step is we converted the grid into centroid coordinate, and we overlaid centroid with census block, and then selecting a grid with the highest score in each census block. For example, the highest score of census block number 011B is belong to the blue one, the with score 16. And its procedure is the same procedure produced in other census blocks. The fourth step is segmentation. The segmentation process is the process of dividing the raster cell of high-resolution satellite imagery into non-overlapping segments or polygons. And the segmentation process produce the arbitrary number of polygons, which is the more variants of pixel characteristic, the more polygons will produce. And considering the reasonableness of the workload, we limit the polygons up to maximum of 5 polygons in each grid. This is the data collection result. We obtain 3.8 million point samples, which is more than the target samples. And the bar shows the distribution of each point sample in each class. It can be seen that the artificial surface has the highest point samples. This is because the determination of the target sample is obtained from census block, which is very strongly influenced by the residential area. After the data collection, then the data validation process. The objective is to ensure the quality of the data collected, and the output is approval of samples points compatibility with its properties. There are this step validation. First, spectral index validation using Sentinel-2. The objective is to check whether a point sample match with its spectral characteristic using NDVI, NDBI, and DWI. For example, if a point's label is plantation class, then the cell value of Sentinel-2 should have the value of NDVI. The second validation is photo validation using convolutional neural network. The objective is to check whether a sample photo match its class label. For example, if a sample point is labeled as plantation class, then the photo must be a plantation photo as well. And the last one is combined validation, which is to obtain the final sample using the decision matrix. Each sample will be labeled as approved, not approved, or manually validated. Approved if it passes both validation, not approved if it doesn't pass both validation, and manually validated if it doesn't pass one of the validation. This is the example of the validation result. The first image is the example of approved sample labeled as rice field, and CNN identified the photo as the rice field as well, and it matched with spectral characteristic. The second one is the example of manual validation. The sample labeled as artificial surface, whereas the CNN identified the photo as non-irrigated crops, and even though it's matched with spectral characteristic. And the last one is the example of not approved, because it doesn't pass both validation, spectral or and manual validation. We obtain this result, 84.33% that pass the spectral validation, 50.63% that pass photo validation, and 41.89% that have to be manually validated. Based on this result, we can conclude this following point. First, Indonesia has a high variety of agricultural land characteristics, such as multi-crops in one land parcel, which may cause uncertainty in defining proper training samples. Second, the different understanding of each field worker regarding the definition of land cover class increases the incorrect labeling samples. And last, the automated validation step is a fast way to filter data of dubious quality from a very large amount of data. Okay, I think this is the end of my slide. Thank you. Back to Kavinda.
Thank you, Ms. Hida. So you took the 12 minutes. Very good. And then I think sharing your real groundwork with the department, and very good. So I will open for questions and any comments. Okay, Ms. Sasha from Indonesia itself, maybe you may have a challenging questions. Okay, yeah. Ms. Sasha, over to you.
Thank you, Kavinda, and selamat pagi, Bu Widya. So
Okay.
actually, I actually hope, not hope, I think you will present another topic for your presentation, like area frame sampling. Yes, area frame sampling is a very good ground truth methodology that you used and already implemented in Indonesia for data collection, right?
Yeah.
And did you use that methodology for validate your research using remote sensing? That's my first question. And my second one is, what's the meaning of the spectral validation? Because I saw that the accuracy is high, but not meet your statistician BPS one,
Yes.
because BPS like to get more than 90%, right? So it means that if DPS already assess remote sensing for data collection to support your data collection, so it means that DPS interesting to use remote sensing data. I'm very glad about that, because for a long time we the researcher from Ministry of Agriculture already have a research and try to use the research to support BPS, especially using remote sensing data, Kavinda. Okay, so it means that we can collaborate to do the research together. And I hope in the next future we can use remote sensing to support data collection for BPS, because we know the remote sensing is very potential to support that, because if we use traditional methodology like Ms. Sangeeta said, that's ground data is need very high cost, right? And also need human resources, and also we need maybe time for collecting the data. I think that's all my presentation, my question for Ms. Widya. Okay, thank you.
Thank you, Ms. Sasha. Either you want to respond?
Thank you, Ibu Sasa. Selamat pagi. Yes, I'm sorry. Unfortunately, I cannot present the topic about sampling frame area, because that's not my authority to do the presentation. The question about spectral validation, right? Actually, to collect the ground data, we hired 57,000 local people to do that, which is they have maybe different concept and definition to understand what's the land cover class. So we cannot using the data without the validation process. First, the spectral validation to ensure the label is correctly in with the spectral characteristic. For example, if the sample labeled as vegetation or for example forest, so the characteristic of Sentinel-2, it should be has the correct NDVI. That's the process to validation the spectra. And yeah, for the spectral validation, we obtain more than 80%. Yeah, that's quite large number, but we have many incorrect labeling in photo validation, because we only reach about 50% that doesn't pass the photo validation, which is photo. For example, if the photo labeled as rice field, but the model CNN model identify the photo is not a rice field. That's the second one validation. I hope it's answered the question, Ibu Sasa. Thank you.
Okay, thank you. It means that spectral validation you compare with the index vegetation, right?
Yes.
Okay. Okay, thank you. Thank
Yeah,
you,
I
Kak
think,
Vinda.
yeah, thank you. Thank you, Ms. Hassan. I think before I give floor to the OAE in Thailand, but I have two questions I think I feel is relevant with that. So I think Anthony put two questions in the chat. First one, I think you talk about you've been using around 57,000 people for data collections. I think Anthony's first questions is, how were the classes of land cover classification determined? So, and is a standardized classification used by Statistics Indonesia? So that is, I think, important questions if you can address. And other one is also, I think you can mention like how frequently you are collecting the ground truth data. So you'll be executing 57,000 people, how often, and if you can give some feedback on that would be nice. Anthony, I hope I address correctly.
Thank you, Anthony. The first question, we follow the national standard. There is a document, national standard for land cover classification, which is we follow that document to identify, to determining the classes, the land cover classes. However, we adjust some definition because we have some difficulty to exactly following that document. Because in fact in Indonesia, as I mentioned before in the slide, we have a very diverse characteristic of land agricultural land. We cannot specify for particular crop. For example, corn. We cannot classify in separate class, corn class or maize or anything that, because in one land parcel in Indonesia, mostly in one period, there is no, most of the land parcel in Indonesia is planting irregular. For example, in maybe in one period is planting with corn,
different
and
crops.
different crop in 1 year period. That's why we cannot classify particular crops in separate classes. And the frequency of the ground truth sample for this land cover, this is the first one, the first project for us to collect the ground truth data. But we have a routine survey sample frame area, which is to estimate the rice productivity, and it's a routine survey. Every year we have to estimate the rice productivity.
Yeah.
The
Yeah, thank you, Vida.
Yeah, okay.
Sorry, number, I mean, it should go annually, right? So that's what I understand, right?
Yes.
Yeah. Anthony, do you want to further continue your kind of questions? So what I understand for the first question is like, I think they are trying to use the land cover classification classes from its standard, but they're trying to adapt. But the question is whether the department is accepted or not. I think I saw Sangeeta's raised hand. If it is relevant to Vida's comments, you can go ahead. Otherwise, I will give the floor to OAE.
Why don't you ask other colleagues for their questions first, since I just raised my hand.
OAE, so I give the floor to you.
Because from your presentation down in maybe 2 points, for the validation process that you use for the Sentinel-2, you try to develop for the 3 index for the NDVI, NDVI, and NDWI. Do you think it is sufficient to classify for the vegetation area and for the build-up area or anything, and refer to the Anthony about the frequency of the ground-truth survey? I have one question about that. For your land cover classification, do you mind on the crop calendar? Because several crops have different planting of date and maybe different on the harvesting. Do you mind for the crop calendar for the classification?
The first question, the confidential to using the spectral validation, right? Okay. Yeah, actually, because we obtained very large amount of data, which is 3.8 million is very large data. We must do something to filtering the data, right? So the spectral validation is the first one. We have to check whether the sample is correct in the right position or not. Yeah, if I'm if the correct whether I'm confident or not, I cannot answer exactly, but that's the procedure. At least with that procedure we can filter fastly. Yeah, and I think that's the proper procedure because we use Sentinel-2 for the classification. The second question, I'm sorry, I've forgotten. Can you read it?
For the second task, for the rank cover classification and refer to the Anthony question about the frequency of your GAU2 data. So I confused that when you have the classification, do you determine on the COP calendar or not? Because the planting is maybe different planting date in the different COP. So you determine on the COP calendar or not?
Actually, we had land cover classification in 2021, and the output used to determine the target sample location in 2022. And in these years, we reclassified the land cover using the ground data collection, which is we cannot share the result now because we're still going on the process. The progress still going on, and that's the story. So using
And also, Ms.
yes.
Vida, I think she also asking that when you decide the ground truth day, whether you try to use the crop calendar as well to see that one, and then parallelly you plan it or not. So I think Thailand they're planning like that. So you see the crop calendar, and then accordingly the zone regional wise they plan the ground truth data collection. Try to align with the crop calendar.
Oh, okay. Yes. Okay. No, the answer is no.
Okay.
We only
Thank you.
collect. Yeah. Okay.
And if any other, yeah, thank you. And if do you have any other colleagues having any questions? If not, I will give floor to Sangeeta for a question. Okay, Sangeeta, you can go ahead. And then also there's additional explanation by Ms. Vida's colleague. You can read about the NDVI and other indexes. I think he explained further.
I think we had Miss Rizatas had a question as well, or was that already answered?
She had a question, two questions in the beginning. We answered.
Okay. So a couple. My questions relate to sample size and to the interpretation of the photo image. So with sample size, you already noted that it's a really, really large sample. About just over 3 million points are validated, and I'm assuming that's done with human beings on the ground. So my question to you is, I understand Indonesia is both huge in terms of geographic coverage, but also very, very diverse in terms of the islands that make up your country. Notwithstanding, 3.2 million is a huge sample size. So have you had discussions on how you could efficiently reduce that sample size? That's my first question. It's okay to say no, but I'm just wondering, because I know that would be a prohibitive cost, especially for some smaller countries, notwithstanding that their sample size will be smaller. The second question is, when you're interpreting the photos, you mentioned in part of your presentation that you use the photos to also validate. Do you have any software or platform that's used to interpret the photos and determine what exactly the category is that you're going to classify it in, or is it largely done manually, or is it done both automatically and manually, and what's the division? So those are my two questions. Thank you.
Okay, thank you. The sample size to validate the photos, the first question, right? The exact number I forgot. 2,000 for each class. Maybe Oji can help me to answer the first question, the exact number of photo validation.
Okay. Is my voice clear?
2,000,
yes,
right?
please.
Okay. Okay. On behalf of Ms. Vida, I think for the photo validation, we have already validated more than 1 million until 2 million photo. So regarding the question about photo validation, we also built the model, actually a CNN model, which uses the convolutional neural network, and we built from scratch. using the Python language, especially using our Fast AI package. Regarding the first question from Ms. Sangeeta about the exact number of sample, actually we can answer that we will say no, because this photo validation is used for the building the agricultural land cover for Indonesia that will be used as the map for the agricultural census. So it will be good if we can take more sample that will be used as the foundation for the next agricultural census. I think that's my answer.
Did we miss the answer?
And actually, you answered a third question that I was interested about the sample of photos you take, but I'm wondering about the overall sample size. You know, whether you're doing photo
Okay.
validation or in situ validation. 3 million, a 3 million sample size strikes me as very high.
Mhm.
And granted, you're not collecting huge amounts of information for each of those 3 million points. But how do you look to reduce the costs of that size of sample or data collection associated with it?
Okay, not all of the 3.8 million we use to we use it for the classification. Each region, we divided the country into region. So it depends on the region. Maybe for example, in Kalimantan, we have to using the training sample larger than other islands, since Kalimantan is the biggest island in Indonesia. Now the exact number, I don't remember how much, but not all the 3.8 million, because after we validate the sample, yeah, maybe more than only a half of that we can using as the training samples. Yeah, sorry, I cannot answer the exact number how much.
Yeah. Thank you, Vida. I think we can get connected if you have further questions. So I think yeah, there are one more questions. If you, Ms. Vida, can answer in the chat would be nice, because I'll move to the next presentation. So we took quite 20 minutes for the discussion. It was, thanks everyone for active engagement. So I would like to move to the next presentation by Ms. Jimin Lee from Statistic Korea, and she is going to talk about using in situ data for deep learning in agriculture area survey. Yeah, floor is yours, Ms. Lee.
Okay, thank you. Hello, my name is Jimin Lee, who works for Statistics Korea Agriculture and Fishery Statistics Department. Thank you for the opportunity to share this presentation. Okay, today I will make a presentation about using in-situ data for deep learning in agriculture area survey. Okay, this is the order of presentation. First, I will explain agriculture area survey in Korea, what kind of survey and how can we do survey. Second, when we do agriculture area survey, we don't do whole survey like census every year. We do sample survey every year. So when sample survey, the survey method are two types. One is RS and the other is field survey. Third, I will explain our deep learning system and training data set and validation. And last part is further work. Agricultural area survey means in Korea, the arable area survey plus the cultivated area survey. And for these two surveys, we do arable land census every 5 years. To apply RS and GIS to agricultural statistics started in 2008, and we had been planning and pilot test for several years. At 2012, we announced the arable area survey using RS. And we started using RS and GIS when agriculture land census since 2014. Last year, we built a deep learning system. It's kind of prototype, and I mean, it's first time, so we need many additions and supplements. We do the arable land census every 5 years. Before 2014, we did 10 years period. But after accepting RS and GIS, the budget was reduced to 1/6 and the survey period was reduced 1/2. Geographic information, the name of PubMap is made by Ministry of Agriculture, Food and Rural Affairs. The PubMap is used as the basic data for the arable land census. We built enumeration district about 2 hectare plus minus 20%, and then performed 9 stratifications on the sampling plane and sampling each layer. And we also reviewed sample stability against the result of the old samples and checked the time series stability. The arable area survey is to survey and be published the area of paddies and field that can be cultivated through sample every year. From 2020 to 2015, the arable area survey were conducted only with RS, and since 2016, field survey and RS had been conducted in parallel. In the arable area survey, out of total of 3,200 samples, 2,200 are surveyed as field survey and 1,000 are surveyed as RS. 6 regional offices and 34 district offices are in charge of field survey, and RS surveys are conducted at the main office. The cultivated area survey is surveyed the area of each crop cultivated in the field 5 times a year. The survey is conducted using a tablet tab equipped with a GIS system for all crops in samples. In November, the cultivated area and the arable area will be surveyed together. The arable area survey and the cultivated area survey are conducted through a sample survey. There are 2 types of sampling survey method. One is RS using satellite images, and the other is field survey using GIS system. Let's take a closer look at the method of survey. In the south, the blue and green area shows the distribution of sample for the agriculture area survey. As mentioned earlier, the arable area conducted field surveys plus RS surveys on 3,200 samples, and the cultivated area conducted field survey on 2,200 samples. In the field survey sample, the target sites are the same. This is a process of arable area survey using RS. The sample area is interpreted visually using satellite images of 1 meter or less. This is our country satellite images named COMSAT and COMSAT. And the large scale change the population is updated. Then the change area is analyzed and the arable area is estimated by the combining the result of the field survey. The arable status of the sample area is double-checked using the latest PlanetScope satellite imagery. The PlanetScope satellite image can be interpreted to check whether the paddies are up to date. Field survey utilized GIS systems. This is divided into the web management program of the main office and the GIS app in the field. Since 2021, all field survey of agricultural area has been conducted through GIS app. The main office distributes survey works, collect result, and link with other systems through the management program. This is part of the functional configuration of the web management system. The division of duty, updating spatial data, and collecting results. And these are some screens of the agriculture area survey app on the tablet tab. You can see these functions: sample search, input survey result, area measurement, memo function, and photo management, such as optimized for field survey. The results save the spatial data as shape files. Now I will talk about the deep learning system, which is being operated as a pilot and the use of field data. The lack of budget and manpower of field survey and the low efficiency and constancy of visual interpretation were constantly pointed out as problems. As an alternative, from 2020 to 2021, a deep learning system is built and is currently in the stage of verifying its effectiveness. The deep learning system was configured to analyze rice, major crop, and arrival land by satellite imagery and aerial image. Rice is a crop growing on a large scale. Training datasets were constructed using Planiscope, which include a large area even if the image resolution is low, and has a short image acquisition cycle. It uses deep learning models such as UNet and DeepNet, and performed functions such as model training using training dataset, model validation, and accuracy. Several functions of the deep learning system were captured on the screen. It can perform various functions such as satellite image management, model management, and performs evaluation. This page is the important page in this presentation. Our goal is to build training dataset using the institute data to compare and validate the result classified as a new image using in the institute data again. The institute data will be accumulated in the same area for 5 years. And in the future, 5 years of the institute data can be obtained again in the new sample areas. So sufficient training data set can be constructed. No security information and no additional budget are required for the institute data obtained by the survey method described above. We are concentrating on rice cultivated area and building training dataset first. The rest is further work. In order to successfully utilize the deep learning system, we plan to continuously build training dataset until next year and discover new deep learning models. In addition, we plan to make effort to acquire satellite images or to support dedicated servers and human resources for deep learning. Thank you for listening.
Thank you very much for the presentation. I think you covered all the activities you do, including data collections and then the advanced satellite classifications and then validation. So I'll open for the questions, and I will Yeah, I will try to stay like until 10 minutes. Questions? Yeah, okay. Over to Jacinta.
Hi, thank you for your presentation. I was wondering which kinds of deep learning methods are you using?
We have several deep learning models. So this year we tried several models. Tried like UNet and DIMUNet and HRNet like that. We continually search which model is has high accuracy. We tried.
Thank you.
Thank you.
Any further questions? Yeah, over to Prachi Bansal.
Hi. I just wanted to ask you that if, machine learning needs copious amounts of training data, as you said, you would need to generate a lot of training data and models to use it. And there's something written that field survey can be eliminated. But given the climate risk and the changes that we are looking at ahead, don't you think field survey can not really be eliminated, even if we use machine learning? I mean, just...
You mean yes, it's too hard to correct training data set, but we tried because we have field survey. Through the field survey, we have institute data. So when we built the training data set, it's like we have some data set with like shapefile and separate image. So we little changes. The standard is the image. So even if the field information is right, but when the screen the satellite image, we change the some information, the crop information, and then we use it. Is that correct answer?
Thank you.
Yeah, Sangeeta, you can go ahead.
So I just wanted to clarify Prachi's question. Prachi, were you asking if it's essential to collect ground truth data in situ?
No, my question was that, we cannot, I just think that one cannot eliminate field survey data. Like, as in with machine learning methods, the idea is that you provide them with copious amounts of training data, and eventually the machine can do what it's supposed to do. There's no need for field surveys. And that somewhere I saw that line written in the slides that field surveys can then be eliminated. So I just wanted to ask that, given the changes that we are seeing in climate change, etc., do we really think that field surveys can be eliminated? That's...
If I can, I think the goal is not necessarily to eliminate, but to reduce.
Yes.
For the simple reason that if you are getting continuously access to new technology, new images, you're trying to expand the range of crops you're covering. Right now, we can't cover certain types of crops. We can't cover multi-cropping and intercropping, right? That may change over time as technology evolves. So I don't think that ground truth, in situ ground truth data will ever be eliminated. And it still appears that one really effective source is through traditional field surveys. But to the extent that which those field surveys can be reduced,
yes,
given that the cost ratio is now switching, that access to the images isn't what's costing as much money, it's actually collecting the ground truth data that's costing a lot of money. If you can reduce either the sample size or the frequency, then that's one mechanism towards making the use of remote sensing more cost effective overall. That's my view, but I would like to have other colleagues who have more expertise on the GIS side also share their thoughts. Over.
Yeah, thank you, Sangeeta. Miss Lee, you want to a little bit comment on Sangeeta's opinion? So she said that we may be really necessary the ground truth data. We cannot completely eliminate. So do you want?
Yes, I agree with her opinions. Yes, in my country, everyone think field survey is too hard. So they want some technical skills replaced to technical skill like RS and GIS. But we know RS is not perfect instead of field data. So we need to combine and save the many correct field data to get high accuracy using RS. So and then yes, so we sometimes some days the field data will disappear, but we can until then we tried to develop our technical skill using RS. Yeah, that's my thought.
Yeah, I think you also in the opinion of the try to reduce the number of sampling and then improve that one. I think I see some communication. I think Jacinta also gave her opinion. Yeah, we are trying to sample the location that we don't have access using remote sensing data. Yeah, I think that's quite everybody's around that. So we try to use the technology, but we'll keep the ground truth, but try to reduce and also use inaccessible areas for sampling and different techniques. That is, I think yesterday also, I think Frank also trying to present that how drone trying to use for inaccessible areas to increase number of points if you go to one location. So this is everyone looking around the same topic. So I think I will keep 2 more minutes for questions if somebody want to raise. I think Anthony, I noticed your questions. There's a question from Anthony asking that how your system handle the mixed cropping areas is challenging, or what is your opinion?
The mixed cropping area. What means mixed?
Anthony is mean by the multi-cropping, or can you a little bit clarify?
Sure. So I noticed in the slides that the focus is on the system of large monocropped areas. So I was wondering, do you also take into account like the smallholder type farms where they have lots of crops maybe growing in the same field? How does your system account for those?
Yes, we have in Korea, we have a very small farmland. So, and it's very complex, and we had many crops in same areas in same land. So it's very not easy to catch the right information. So we have a standard. If we the standard is when we got the satellite image, that day is we interpreted that period. If paddy is not rice, it's not paddy, and like that. And so we selected by satellite images times. Is that answer for you?
Yes, thank you.
Thank you.
Thank you, Ms. Lee. I think giving answers to all the kind of clarifications. I believe Sangeeta's hand raised is from the previous one. So Sangeeta is going to moderate.
No, I do actually have one quick question.
Okay, go ahead.
It doesn't need to be answered right now, but I do want to drop this. We've just had 2 presentations from National Statistics Office. We have another one from the National Statistics Bureau of China coming afterwards. What I often see is that it's not in fact the National Statistics Office that's leading the work in a country on the use of remote sensing for crop statistics. That certainly has been the case in the presentations we've seen. So I really appreciated, Ms. Lee, your putting in context of how the total agriculture statistics program is planned. But where that's not the case, how do statistics offices, and we have colleagues from statistics offices here, how do you step into the area of using remote sensing for crop statistics? And how do you engage with the ministries in your country that are leading? And conversely, for Statistics Korea, Statistics Indonesia, and the National Bureau of Statistics for China, how do you bring in your ministries that are the key users of your output, such as your ministries of agriculture? How do you engage them to get them involved in your work? And we saw a question that came to Dewey from Statistics Indonesia earlier. Like I said, I don't think we have time to answer that question, but I'm wondering if we can formulate this question for our discussion period tomorrow, that last hour tomorrow, because I think it would be very useful to have that discussion around policy and governance, if that's okay, Kavinda.
Okay,
Yeah.
I will do.
Yeah, thank you, Sangeeta, giving the more insight for the discussion, constructive discussion we could do in tomorrow. Ms. Lee, if you can also around for tomorrow, the second session for the discussion would be very nice. So you also have a complete system in place, so you can give your insight. Sangeeta, if you are also around, maybe I will give the floor to you.
Thank you very much. So colleagues, welcome back from your break. As you've noticed before this break, we had presentations from 2 statistics offices in the region. Will be followed by another presentation from the National Bureau of Statistics of China. And to make that particular presentation, we have a colleague who has a great deal of expertise in this area, Mr. Guo Hang. Mr. Hang will be followed by a presentation from Dr. Jacinta Holloway-Brown. Dr. Holloway-Brown is from Australia. Australia has a very interesting model as well in using remote sensing and Earth observation data for crop statistics. In their particular case, the Australia Bureau of Statistics has partnered with lead ministries and agencies within Australia who manage the work. Jacinta herself has a very interesting background, I think, which is worth drawing attention to. She has degrees in economics, statistics, and journalism. She's also worked closely with the UN system in terms of the Big Data Task Force on Earth observation data, and has conducted training in 3 different countries in the world, including in Bangkok, Thailand. So without further ado, I would like to first turn the mic over to our colleague from China, Mr. Hang. Over to you, please.
Hello, everyone. I'm glad to attend this meeting. The topic of my presentation is the remote sensing applications for agriculture statistics in China, supported by ground survey data. Since the beginning of this century, the National Bureau of Statistics has vigorously promoted the application of modern spatial information technology in statistical work and stuck to supporting the general principle and scientific research, preparing projects and progressing steadily, which are advanced general in agricultural statistical remote sensing work. Through nearly 300 years effort, it has formed a remote sensing application model for agricultural statistics of big data and small data. And the big data refer to satellite remote sensing data covering a larger area, which is used to obtain a larger scale area and yield. Small data refers to small scale ground truth data. The combination of big data and small data can infer the required agricultural statistics. With the development of remote sensing applications for agricultural statistics, it has continuously upgraded the means of collecting ground-based data and has initially formed an integrated air-ground collection system, which has realized a major change from household survey to ground survey. From 2003 to 2015, with the support of the government, the National Bureau of Statistics preliminarily established the remote sensing environment and yield estimation operation system of grain crop planting area in May grain producing area. Since 2009, Liaoning, Jiangsu, and other places have been organized to carry out agricultural statistical remote sensing applications and agricultural sampling service on the ground. since 2014. The National Statistics has carried out a survey of cotton area in Xinjiang using satellite remote sensing technology to meet the need of the Chinese government to formulate cotton production policy. During this period, the means of collection ground to state changed rapidly. The survey means has undergone change from home visit, on-system measurement, GPS surveys mappings, to survey using directed survey tools, PAD. With the support of special survey tools, it has realized the rapid survey directly baseline. Based on satellite remote sensing measurement data and the strong ground investigation cooperations, the NBS has continually improved the identification accuracy of May food crops and the cotton soil area, and achieved satisfactory progress and good results. In the third National Agricultural Census in 2016, the National Bureau of Statistics specially formulated a survey plan for remote sensing measurement of crops. It made full use of satellite remote sensing image, UAV, aerial photography, and ground data collecting to conduct remote sensing measurement and field investigations on the soil area of major crops in the country. It replaced the census method of conducting household survey in previous census, reduced the organizational difficulty of the census work, and greatly improved the objectivity and accuracy of the census data. In the progress of organization and implementation, the National Bureau of Statistics divided mainland China in two types, that is A and B, according to the characteristics of agriculture, planting, and the difficulty of carrying out the work. LA were mainly 22 major grain producing provinces. They were used to carry out remote sensing measurement of crop planting land in the province, special distribution measurement of May crops in the province, and the precise measurement of the area of May crop in selected village level unit. Other area was classified as B. They were used to carry out remote sensing measurement of crop planting land in the province, and the special distribution measurement of May crops in the province. Our remote sensing measurement tasks have put into use more than 110,000 satellite remote sensing images, mainly China, Gaofen 1, Gaofen 2, and Beijing 2. The National Bureau of Statistics selected more than 20,000 survey areas and more than 110,000 survey square nationwide. It conducted on-the-ground survey through special survey work, and in some areas, drones were used to conduct ground survey. It had carried out more than 10,000 shooting missions and obtained more than 5,000 pieces of survey data. On this basis, it had obtained accurate data on the planting areas of major crops in different provinces across the country. On the basis of the large-scale remote sensing application of the Third National Agricultural Census, Agricultural Statistics Service will continue to promote the construction of the integrated air-ground survey system from three aspects. First of all, agricultural statistical survey need to do a good job in the construction of ground survey outlet on the basis of the full coverage of remote sensing survey. Results established by the Third National Agricultural Census. The survey needs to be combined with the result of the Third National Land Census, and according to the characteristics of agriculture's production in various places, to build village-level outlet that meets the need of provincial and country-level agricultural survey. The survey needs to adopt a simple random sampling method in village-level outlet and select 3 grade units of 200 meters plus 200 meters respectively at the sample square of the ground survey. And the second, agricultural statistical survey needs to do a good job in the construction of survey information capabilities for ground survey. It has specially developed survey tools which can realize the full set of functions from survey location search, offset comparison, information feedings, and recording to survey result management. For UAV survey, it mainly focused on Dajiang UAV developed a corresponding application system, realized the application system from ground image shooting, sensors, identifications to level-by-level verification, and explored the application system of deep learning technology in image recognition. Application which greatly improved the efficiency of image recognition. And thirdly, agricultural statistical survey need to ensure satellite image data results for agricultural statistical remote sensing application. It has participated in the domestic high-resolution image program so as to obtain stable, medium resolution and high-resolution satellite image guarantee. And the use of domestic image data in daily work accounts for more than 90%. With the support of such a survey system, in 2018, the remote sensing work of agricultural statistics has been incorporated into the statistical reporting system, and the area survey and growth monitoring of major grain and cotton crops in China may producing areas are regularly carried out. In recent years, the National Bureau of Statistics of China has actively expanded the depth and the breadth of the application of spatial information technology in statistical work in order to obtain more objective and accurate survey data. For example, in the monitoring of a crop production situation, it has studied the use of satellite remote sensing data, historical regional yield statistics, ground-based data, and so on, in order to form an index indicating the trend of crops yield change, serving food production management. In terms of improving grain yield survey method, it has studied the use of multi-source and multimodal remote sensing indices to screen out crop yield sensitivity characteristics, modeling with actual cutting data to obtain a crop remote sensing yield estimation model, and grasping crop yield 1 month before harvest. In the livestock survey, it has had two explanations. One is for grassland animal husbandry survey. It has studied the use of unmanned aerial vehicles ground survey and high-resolution remote sensing to conduct flux survey, which solving the problem of livestock survey in grassland areas with difficulty traffic. Another is to carry out remote sensing survey of pig farm. It has developed a deep learning artificial intelligence model to identify the spatial distribution of farm use satellite remote sensing image. At the same time, it has combined certified survey data to develop a model to evaluate the pig breeding capacity of individual farms. Next, the National Bureau of Statistics of China will focus on improving the integrated air-ground survey system, promoting the construction of digital and intelligent remote sensing application capabilities, improve the ability to quickly investigate ground-based data, consolidate and expand the application field of remote sensing technology in statistical work, and improve the ability and level of statistics to serve the country. That's all. Thank you.
Thank you very much, Mr. Hang. Do we have any questions from the floor? I see that Ms. Rizatas has raised her hand. Over to you, please.
Thank you, Ms. Sangeeta. So I have a question about the yield estimation that use BPS using remote sensing data. Do you have implemented this model for the estimate your paddy production? And then so what's the accuracy? Because actually we used it and we already have the model, and we use a Sentinel-1 for predict the yield estimation, even though the authority to publish the yield, paddy yield in my country is BPS, but we have this model, and we have discussion with BPS to potentially or to use this remote sensing data. So do you have any high accuracy for this one, and what kind of model and data you use? Because we also have to consider to use this remote sensing data for crop insurance, because we try have pilot project to use it using the yield index for the crop insurance, and then I think it's very good model if we can apply we can implement this one for BPS and also for crop insurance. I think that's my question, Ms. Sangeeta.
Thank you very much. Over to you, Dr. Hang.
Can you please repeat the question? Briefly.
Okay, I can repeat my question.
Yes.
So what's data, satellite data you use, and also what kind of model you use, and what's the accuracy of your model? That's my point of my question.
Okay. In our project, we have introduced the 3 levels remote sensing. High resolution remote sensing, medium resolution, and also the coarse resolution in remote sensing image. And for our productions, we have we use the wall-to-wall and medium remote sensing image to extract the crop land distribution, and then at the province level. And then we use we construct the sampling framework to and then we use the two levels, two-stage sampling process. The first one is the first step is to we choose we supplement the village plot and village plot at the first stage and then in the sampling stage we choose the 200 plus 200 multiple 200 plots in sampling method. Then from this process we use the PET tool or UAV technology to measure the plots, and then we introduce the ground truth data and the remote sensing together to estimate the accurate estimation. And maybe that's we introduce the remote sensing how to use the remote sensing image and how to remote sensing technology in our statistical project. Thank you.
So for a yield estimation, so how many times in 1 year you publish the yield estimation established data to government? Because in my country is 3 times. That's right, Ms. Vida. So it means if we use a very high resolution data, I think it's costly.
For our project, for our aim, and for operation field, for the operation field, and we introduce the remote sensing in the crop accurate estimation. So maybe for our for this stage, we use the one time for accurate estimation, and we have covered we have covered 13 provinces.
Thank you. If I can interrupt, we have our next presenter who actually has to leave shortly after the EGM for another meeting. And given that she's coming from Australia and has probably not yet had lunch, I'm going to propose that we have Dr. Jacinta present next. So we have a bit of time for questions and we can come back to additional questions for our colleagues from the National Bureau of Statistics. So thank you, Dr. Hang and colleagues. Please do stay with us. Dr. Jacinta, it's over to you, please.
Thank you very much. So thank you very much for having me, and thank you, Sangeeta, for the really nice introduction earlier. So I'll be speaking about some ideas from a discussion paper that I've put together for this meeting, along with distinguished Professor Kerry Mengersen. So she is unable to be here today, but we've collaborated on this discussion paper together. And I'll be speaking about statistical machine learning for adaptive ground truth sampling design. I just wanted to mention too that I'll be speaking in this example in the context of the SDGs and looking at forest cover. However, all of the ideas are translatable to any official statistic or SDG that we can monitor from satellite images. So definitely relevant to crops. And previously, so I'm currently a researcher at the University of Adelaide, but prior to that, I worked at the Australian Bureau of Statistics for 7 years, including with the satellite imagery task team through the UN. So I have a bit of experience on both sides of this problem. Right. So the Sustainable Development Goals, we know all about these. They're these really important high-level objectives that we're trying to get to by 2030 for all countries in the world. And within these, we have different indicators. And it's really important that we're able to monitor our progress towards these SDGs in order to make our way to achieving them. However, there are prohibitive costs of field data collection is a key factor that's preventing or limiting some countries from monitoring the SDGs. So satellite imagery analysis provides a solution to this issue in terms of the cost. As we already discussed throughout this meeting, satellite images are available for free globally. They're a really useful open access data source. They allow us to find insights over large, remote and restricted geographical areas. So there are some places in Frank's presentation yesterday, I think it was too, he gave the example of not being able to drive to a particular area to collect ground truth in person. There are also situations where it might be too dangerous to access an area because of natural disasters that have occurred. Maybe there's flooding or there might be conflict in a region. And so satellite images allow us to get this bird's eye view of places that we can't physically get to easily. And as the sensors become more advanced, as they constantly do, we have data at higher and higher resolution, so we can see better and better what's really on the ground, and we get that even more frequently. So at the moment, the Sentinel-2, you can get new images for the globe every 5 days, and there are sensors that you'd be able to get it even more frequently. So satellite images have huge promise for SDG monitoring and for official statistics. And indeed already in use by groups like the UNFAO. So remote sensing satellite images, everything like that has been shown to work for monitoring SDGs. The Committee on Earth Observation Satellites, this international group, CEOS, have produced reports and found that particular SDGs are able to be monitored using these types of images. So just for instance, on this slide, we know that we're able to do crop area estimation and crop yield, for example. Water quality monitoring is possible in some cases, and also forest cover change over time. So we can see deforestation, we can look at the amount of forest cover over an area that we have. But a problem that I think was also mentioned previously in this meeting is missing data due to cloud cover. Okay, so this animation is from the NASA cloud product, and it shows the average cloud cover for each month over a number of years. And so everywhere that we can see white, that's cloud cover, and where there's blue, we're able to see the ground from the satellite. However, this cloud cover is a really persistent problem, particularly in a lot of the areas where we want to use satellite images to do our modelling. There was a study done of 12 years of satellite images, and it found that on average at any given time, 2/3 of the world is covered by cloud. So that's huge. That's a huge missed opportunity to be able to monitor things like our crops, our forest cover, our important outputs for our SDGs and our official statistics. So we need to find ways around this. So missing data due to cloud cover makes the task of constructing accurate land cover maps, which is something a lot of us are trying to do, especially challenging because we have these huge holes that we're not able to fill in easily. And ground truth data is important for our model validation, and the difficulty of balancing the limited resources that we have to collect ground truth and the minimum data that we need for statistical rigor is an ongoing issue. So what we're proposing is that we can use selected statistical machine learning models and their outputs to adapt the Earth observation analysis pipeline. So when we're looking at an area of interest, we've seen in other presentations in this meeting, so we make a ground truth sampling plan and select areas that we want to go to collect some data in the field. We also need to think about, do we have some satellite images or image products available? And so what I mean by satellite image products, these are pre-processed land cover maps or images that have already had the cloud gaps filled in. Unfortunately, these are not available for all different types of land cover maps. They might not be at the resolution that you need it or specific enough. And sometimes they simply don't exist for the area of interest. So when that's the case, we need to work with the raw satellite images that will have missing areas due to cloud. From there, if we're using the images, we can perform our pre-processing ourselves. So that includes filling in the gaps from the clouds, performing our own calculations. So maybe that's calculating NDVI, our normalized difference vegetation index, measure of greenness that allows us to identify things like crops, different types of forest. And then we have a complete image that's ready for analysis. So at this stage, we can fit a machine learning model. And then what normally happens is we get our model results. We validate how accurate or not the model is using the ground truth that we've collected in the field. But what we're proposing is that at the next step, we add another step to this pipeline where we adapt our original ground truth sampling plan based on the validated model results. So adaptive sampling is useful in an SDG and an official statistics context to efficiently prioritize ground truth collection over really large areas and over time. Adaptive sampling design, if you've not heard of it, is commonly known for its use in medical trials. And so it involves changing our experimental designs as we go in response to collected data and outcomes. And we do this because we want to reduce the costs of running the experiment and to improve the efficiency while we're still able to maintain the validity of the study overall. And so this idea has, I think, real promise for planning ground truth collection to monitor SDGs and official statistics using satellite imagery. So under an adaptive sampling approach, we might take our baseline stratified sample design that we start with for our field data collection, and then we augment that by doing some additional, more targeted sampling, depending on what our aim is. Like, what are we trying to learn about the statistic or the area that we're focusing on? So for example, in this table, so if we wanted to improve the predictions of our area of interest, and we have some underrepresented areas and small classes that we're not identifying very well using the model, then we could do some targeted sampling of these specific areas in the next iteration of ground truth collection. We can also increase the sample size of our current stratified design, target specific areas to reduce our overall prediction uncertainty. Or for instance, if we want to gain knowledge of an area that we haven't sampled before, we could use the results of a model to plan our stratified or our cluster sampling approach. So what are the kinds of methods that I'm talking about? So I'm not suggesting that any method would be useful for this adaptive sampling planning. There are some really important considerations because ultimately we're trying to still produce results that are statistically rigorous, that we can rely on and that we can tell our users that we're confident about. But we also need to have methods that are scalable to the number of pixels in the satellite images. And we have two key constraints to performing the analysis, and those are data availability and then access to technology. So in terms of data availability, we have a method that I'll speak about, spatial random forest, and that underpins our overall method. The great thing about this spatial random forest approach that we developed is that it works really accurately based on absolutely minimal data. So in any satellite image, even if you have missing data from clouds, you will always have the latitude and longitude, so the location of each pixel. And so by training our model at the edges of clouds in images, so the edges of the missing data, we're able to get very accurate predictions of the missing data, the missing pixels, just by knowing where they are. That's actually able to tell us a lot of information. And then the other side of it is technology. So our method doesn't require high performance computing and can be run on a laptop for millions of pixels. So we can get predictions for 1 million pixels in less than 3 minutes, just on like the laptop I'm using right now, which is nothing fancy. And I think that's really important because some methods require like cluster computing or high performance computing that not everyone has access to. And I think that any solution that's going to help us to better monitor the SDGs and official statistics at lower cost, but still produce rigorous results. It also needs to be accessible for people. We don't want to be automatically excluding some users just because they may not have particular new technology and infrastructure. So I'm going to speak in really high level sort of detail about the method that we've developed and that I'm proposing can be used in this, this pipeline to make adaptive sampling designs. I don't have time to talk about it in technical detail. If you're interested, this is the title of the paper that I will sort of be speaking about a little bit. So it's called Interpolating Missing Land Cover Data Using Stochastic Spatial Random Forests for Improved Change Detection. So our method, I'll just call it SSRF for short, just so that's easier. So it provides predictions of land cover, even when we have missing data due to clouds. But importantly, it also quantifies our uncertainty of these land cover estimates. The uncertainty is introduced at 2 points. So because it's a model, there will always be some type of error. So we're measuring that error from the model. And we also incorporate observed images from the past. And then we do a weighted average of these two things. And so we're also accounting for error that will be introduced because we're looking at different images over time. So we're assuming that what happened in the past is informative for what we're looking at in the future, but we know that that might not be the case. So we're trying to account for error in 2 ways. And this uncertainty measurement is really essential, especially when our ground truth is limited, which is often the case, and we have large amounts of missing data due to the cloud problem. Yes, and so our method can be used for any satellite image in any region, provided that we have some training data, whether that's in the current image or in the past. And we can use it to prioritize field data collection by highlighting these areas of uncertainty. Our method at a high level in 3 steps is that we take random forest, which is a really effective decision tree method. It's been proven for many years to work well and be accurate for satellite images. We then add spatial information, the latitude and longitude we can get in any free satellite image, and we train our model on observed values that we can see at the edges of any missing sections. And then we layer that into a stochastic framework. And so by putting all of these things together, in the end, we get both a classification of each pixel. So whether that might be its crop, for example, its forest, its wheat or its barley, that type of prediction, we get that. And then also a probability. So it's, 90% probability that this pixel is wheat versus a 10% probability that it's barley, just as an example. And the workflow for our method is summarized here. So we take, for any case, so if we want to fill in the missing section in this cloud, so this little area in the middle of the top image, we would also then take an observed image that we might have, ideally as close in time to the image we're trying to fill the data for as possible, but if it's older, that's okay. From the raw images, we then calculate NDVI and our class variables. In our case study, we were looking at NDVI, but you could use something else if you wanted to. From here, we create training data sets, which we use to train the model. That's how it learns the different features and spectral signatures of the different types of land cover. And then we have these two components that go into the next step of the model. So we fit a spatial random forest, where we take information about the neighbors of all of our missing points and use those to fill in what's missing. And we get probabilities of land cover class from the random forest. And then we also include prior data from a previous image. So this would be our image here, B, that's observed. And from these two things, we weight them, we look at them together, and we construct this conditional probability. So we're basically saying, given what the pixels looked like in the recent past, and given what our model is saying it looks like now, combining these two things, what do we think these pixels look like? And what is the probability that this is what it is, and what is the probability that we're wrong, which I think is really important, especially when we're modeling using satellite images. And so the results then are these probabilities of land cover, as well as a classification into land cover type. So in terms of mapping uncertainty, so this plot shows, all right, so these two panels, they are probabilities for the same random sample of pixels. So this is just an example of a sample of them. You could do it for the entire area and this whole section would be filled. You wouldn't be able to see any white. So we can use the results of our model to produce maps of predictions, highlighting our areas of high and low certainty. So for this example, in the right panel, we have probability of the pixels belonging to the pasture land cover class. If the pixels are light blue, that means the probability is close to 1. The model is quite certain. If the pixels are really dark, like a deep navy, then the model is saying there's a very low probability that those pixels belong to the pasture class. In this example here, for the same sample of pixels, the probability of forest, in this center here in the orange oval, I've just tried to highlight that there is more uncertainty. So the probability of these pixels belonging to forest is around 0.5, but there's also a low probability that some of them are pasture, so they probably belong to another class. The point of this is really to show that depending on your threshold for risk, and this will be different depending on the output that you're looking for, the type of official statistic and what it will be used for, we can set different thresholds on the probabilities to highlight areas that are more important to be certain about. And so if the model is uncertain, we could prioritize these areas to go and collect field data. So the results, such as the ones I just showed you, they're produced at pixel level and they're geo-referenced. So we know the latitude and longitude of all of the points. So we can plot these in various ways. So really this would not be the ideal use of them. In my opinion, what I think would be much more useful is to layer these predictions over a map of the ground truth samples that have been taken and the corresponding satellite image, and then taking these 3 layers of information together and possibly information from an agricultural survey or some other source of information, we would be able to combine these things to strengthen our knowledge about the areas that we're interested in. And then we can identify areas where the ground truth and the model agree and disagree. So by taking all of this information together and highlighting where the model is unsure and comparing that with the ground truth where we know with boots on the ground what it looks like, we can inform adaptive ground truth sampling designs. So we can change our sampling needs and approach as we go based on the things that we learn about the area over time. So I'm almost out of time, but I'm nearly done. So to summarize, adaptive sampling design for ground truth collection holds promise for increased and improved SDG monitoring by informing how we can allocate our limited resources. We're proposing adjusting the Earth observation analysis pipeline by using results from selected statistical machine learning methods, such as the one I just showed you, our stochastic spatial random forest, to inform adaptive ground truth sampling. Our method is accurate for satellite image analysis despite cloud cover, and it produces probabilities of land cover classifications at a pixel level, as well as classifications. So if you're interested to know more detail about the model, I can refer you to some papers about it. So by having a hybrid traditional and model-based approach, we can create adaptive sampling designs that are more responsive to the information that we gain over time, and we can allocate our resources to collect ground truth more effectively. And in future research, my plans are to do a case study using this approach, combining the probabilities and known ground truth from the field and the satellite images. Okay, thank you very much for your time. And these are some papers that are relevant to the talk if people are interested. Thank you.
Thank you very much, Jacinta. And of course, we will be making all of the presentations available on the website, which will be shared with everyone. So with that, can I turn the mic over to colleagues who may have questions, both for Jacinta and for Mr. Hang from NBS China. Maybe I'll start with one question. Jacinta, do you and Carrie ever do training on the use of these adaptive sampling methods?
No, we haven't yet. I would really love to be able to collaborate with someone to do a case study on this and see if practitioners who do ground truth collection find it useful, because these are just ideas that we have, and I could see that it could be really helpful, but I have never tried it in practice. But if people were interested and it would be useful, then I think it would be excellent to do training about it.
Okay. So I'm going to open that opportunity for a further discussion. If Carrie and Jacinta are willing to help in actually applying this method, and there are colleagues who would be interested in applying these methods in their own country context, if you could follow up with discussions on your part, come back to me and let's see if we can develop a small proposal to do this. I do see, Anthony, you have your hand up. Over to you, please.
Hi, thank you, Sangeeta. I have a question for Jacinta. I was wondering, in the model that you presented, does the model take into account the number and mix of classes within the selected cluster area? And I was also wondering, is there kind of a minimum threshold of like one LEN classification cluster that you look at? I'm just thinking in terms of kind of like the Pacific Islands, where their areas are relatively small with very high mix of classes within a given area. Thank you.
Yes, sure. That's a really good question. So I did a sensitivity analysis on this in a paper looking at how many classes for the spatial random forest. That's the model piece of it that feeds into the stochastic framework. I think unless you have a lot of because the problem is the missing data piece of it too, right? Because you might have 10 classes, but you might have lots and lots of data about wheat, for instance, but you only have like a very small amount of training information about, I don't know, sorghum or something else, or forest. And so a lot of that in the model side, it sort of comes down to luck of what you're able to observe at the time, and that's a problem. So that's why using the combination of the image from previous time points and being able to look at what you've seen, particularly, that can help us to pick up some of the smaller classes that we're missing. The accuracy of the model, the random forest piece of it, it does struggle once you get to about 10 classes. And so that's when, in those cases, I think either more available visible image is important or to rely more on previous observations. Sorry, what was the question about the threshold for the cluster?
When you're looking at a particular land classified area, is there a minimum size that you should be looking at? Because I was thinking the case from the Pacific Islands where it's a very small area with high mix.
Yeah, sure. So in those instances, we wouldn't do just like one model for the whole area, like we would do localized trained. So because that would be multiple satellite images, of course, and that would need to come together. So I would recommend doing like a localized training and prediction on each of those smaller islands as their own like mini case, I suppose. Yeah. Does that answer the question?
Thank you.
Great, thanks.
There is a question from GIC for Mr. Guo. It says the livestock monitoring study is particularly interesting. I was wondering if you used thermal imaging to visualize the livestock. Also, how did you account for livestock that were beneath tree canopies or the roof of a structure? So this is for our colleagues from NBS China.
Okay, thank you, question. Let me introduce the technology briefly in detail. And if you want to detect the peak in the farm, and in our technology process, we use the multi-source information remote sensing to extract the to map the distribution of the farm on the farm, and then we can measure the size, such as the areas we can count, and then we can measure how many pigs can be raised in this set on buildings, and then we can make a model that correlates the size on pig and the farm and the building size together, and then in this technology, we can get the conclusion that from the remote sensing image, from the remote sensing technology, we extract the size on building directly, and then infer the size on the pig. How many pigs can be raised in this farm? That's all. Thank you.
GIC, has that answered your question? Yes, they have said yes. Any additional questions? So with that, I'd like to thank everybody for their participation today, for the very good presentations. There's certainly a lot of food for thought. And obviously from the questions that were asked, need for improved and continued discussion and collaboration in this really important area of work. So I'd like to thank everybody again. So Anthony and Kavinda and Dan and Frank, thank you all for another really productive day.